Hello everyone. Good afternoon. Today I'm going to discuss functional dependency concept based Armstrong rules. So these Armstrong rules help you to find out the equivalent sets, the minimal cover, and also they'll be help the key of a relation given a set of functional dependencies. So friends, let us begin. So I'm going to discuss today what are called as Armstrong rules. So here, first of all, we'll discuss the simplest Armstrong rules. The first three rules identified as IR1, IR2, and IR3. Now, what the first inference rule tells is that if y is part of x, then x functionally determines y. So this is a kind of trivial functional dependency. So there is not much involved in this. So this is the most basic inference rule. What is more interesting is the second inference rule. It's called augmentation rule. It means if you have a functional dependency x arrow y, and if you add one attribute z on both sides, then the functional dependency still holds. It means x z arrow yz holds. So by adding the same attribute on both sides of a functional dependency, the functional dependency still holds. So that's pretty much clear. The third one is transitive rule. If x determines y and y determines z, then it implies that x determines z. So these are the three basic identities and they are termed as Armstrong rules. I hope these three concepts are clear with you, but we need additional inference rules. They are termed as IR4, IR5 and IR6. As you can see down here that we have IR4, IR5 and IR6. So let's look at these additional functional dependencies. So the fourth functional dependency is called as decomposition rule. That is, if you have x arrow y z, then you can write it as x arrow y and x arrow z. It means the right hand side set of attributes can be decomposed and the x, the left hand side, remains the same. Okay, so this is the fourth inference rule. The fifth inference rule, if you have x arrow y, which is the reverse of the rule number 4, that is x arrow y and x arrow z, then we can write it as x arrow yz. So this is called as union rule or additive rule, and fourth one is called as decomposition rule. The last one is very important. This is called as pseudo transitive rule. So this is very important when it comes to finding the equivalent sets and minimal covers. So pay attention here. So if we have x arrow y and wy arrow z, then you can replace this y by x. So this implies that wx arrow z. So in place of y, you're just replacing x because x determines functionally y. So this is called pseudo-transitive rule. So there are 6 inference rules. In fact, there are 8 of them. But for our discussion, these 6 inference rules, that is rule number 1 to 6, are important. Hope you are clear with these inference rules. Let us see the application of these subsequently. Now, before we move on to see some of the problems that you all are facing, so let us cover the fundamental concepts. In the exam, there will be question on finding equivalent sets of functional dependencies. So this is the topic of discussion now. So what is this equivalence means? Before that, we need to understand what is called as cover. So as you can see through the definition here, a set of functional dependency F is said to cover another set of functional dependency E. That is, you are given a set of functional dependency F. So this is a set of functional dependencies. Let us say F1, F2, Fn. And you have another set of functional dependency E, which is E1, E2, Em. So we have two sets of functional dependency. Remember, each of these functional dependencies is of the form x arrow y. Okay, so F1 doesn't mean just one as set of attributes. It is a set of attributes on both sides of the arrow. So these are the functional dependencies here. Now here the definition is F is set to cover E if every functional dependency in E can be inferred from F plus. Now what is this F plus? Now given a set of functionality F, you can deduce some more functional dependency by applying the above rules here. So the inference rules can be applied to generate F plus. It means F plus will contain original set of functional dependencies, but some additional functional dependencies F dash, which are inferred from the inference rule. We'll see an example of finding F plus. Likewise, you can also find the E plus, which is original set of functional dependencies which are given to you, plus the derived functional dependencies, which is E dash, by applying the inference rule to these functional dependencies. Okay, so F is said to cover E if every functional dependency in E can be inferred or deduced or derived from F plus. That is, the F plus is called closure of F is F plus. It means F plus contains every possible functional dependency which can be deduced from F. Okay, so now this is what is the cover. Now it might be a case where F is going to cover E, and conversely E might also cover F. It means every functional dependency in F, every FD in F can be inferred from E plus, not F plus, E plus. Okay, so if this is the case, then we say F and E are equivalent. If every FD in F can be inferred from E and every FD in E can be inferred from F both ways, then we say these two are equivalent. Okay, so let's see an example of this. So consider this example here, right? So in the exam, you may be given a problem like this. In fact, this is what is given in one of the question paper that I shared with me. So look at this example here. You are given F. What is F? A arrow C, AC arrow D, E arrow AD, and E arrow H. Now we have to check whether F is going to cover G. Instead of E, he has given G, so don't get confused here. So G is given as A arrow CD, E arrow H. Now we have to check whether these two functional dependencies are equivalent or not. The way to do that is you first find out F plus. That is, you know F, you are given F. What are the other functional dependencies you can derive from F? From AC you cannot derive anything, but from AC arrow D, by applying pseudo transitive rule. If you remember, we had something like X arrow Y and WX arrow Z. We could replace X by Y, so WY arrow Z is what we got. So similar situation is here. As you can see, this is what is WX arrow, WY arrow Z is here. Should take it as WY and it should be WX arrow. So as you can see, this is WY arrow Z and we have X arrow Y here. So as you can see, you can replace this Y, that is C, by A. So we replace C by A and we get it as, so A is A itself, so A arrow D. So from these two functional dependency we derived A arrow D. Okay, now using decomposition rule we can write E arrow AD as E arrow A and E arrow D. Okay, of course we have E arrow H, and initially we had A arrow C also. So total number of functional dependencies are all these. So this is what is your F plus. Okay. So in the original functional dependency, we have A arrow C, which is here. We have AC arrow D, you can include that also. AC arrow D. Then E arrow D is replaced by this also can be include is EA, ED, and EH. So these are all the functional dependencies we can derive, and that is what is your F plus. Now we have to see whether these functional dependencies help us to cover G. What is G? G contains A arrow CD. Now we know that A arrow CD is nothing but A arrow C and A arrow D, but from F plus we have A arrow C and also A arrow D. Okay, we know that if you have X arrow Y and X arrow Z, we can write it as X arrow YZ. We have seen this. Okay, so here since A arrow C, A arrow D, we can write it as A arrow CD. It means from F plus I could derive A arrow C, A arrow CD. Similarly, what is the second functional dependence we have? E arrow AH. Now we know that we have E arrow A here. We also have E arrow H. E arrow A and E arrow H. When we have these two, we can write E arrow AH. What is the rule I am applying here? If you go up here and see the inference rules that we studied, X arrow Y, X arrow Z equal to X arrow YZ. That is inference rule 5 is called as additive rule or union rule. Okay. So by applying additive rule, I could prove that every FD in G can be inferred from F. So F covers G. F covers G. Okay. Now that's the first part. And we can define minimal cover also. Minimal cover means what is the minimal set of FDs which are required to cover G. So here we saw we require this FD, this one, we require these two. So only these four FDs are required to prove that F covers C. So this is the minimal cover. Other FDs are not required. Okay, so you have a concept of minimal cover also. Clear now? Hopefully yes. Now we have to prove that G covers F if G and F are equivalent. So what is given to us in G? We have to write down first. So we know that G A arrow CD and E equal to A arrow H. And for further clarity, let me write down F also. So F is given as A arrow C, AC arrow D, E arrow AD, and E arrow H. So as you can see here, we have too many functional dependencies, and can we really derive these functional dependencies from G? Okay, so that is what is we have to see. G covers F. It means every FD in F should be derivable from G. So we know that G contains the function dependencies which are here. First functional dependency, A arrow CD. So can you not write it as A arrow C and A arrow D? Yes, we can. So as you can see, we derived first functional dependency here. Isn't it? Okay. Now, the second one is we have to somehow show that AC arrow D. Okay. So let us write down the other functional dependencies using the second FD in G, that is E arrow AH. So this also can be used using decomposition, E arrow A and E arrow H. Okay, so as you can see, we have covered one more functional dependency here. Okay, So two functional dependencies are covered, right? Now we know that E arrow AD. So E arrow AD and E AC arrow D is what we have to prove. Okay, and add C on both sides. So we get AC arrow CD. Okay, or AC. Yeah, we only know A arrow D here. Adding C on both sides will get as AC arrow CD. Okay, and we have to prove that AC arrow D only. Now, using any of the FDs, can we do that? Is what we have to check. If you have A arrow CD and if you add C on both sides, you get AC arrow CD. AC arrow CD. So you can write it as AC arrow C and AC arrow D. Okay, so thus we can prove this so very simply. So sometimes you get stuck. So we proved that all the functional dependencies in F can be covered by G plus. Okay, so it's so very simple. You have to add C on both sides. You get AC arrow CD. Okay, and this AC arrow CD can be split as AC arrow C and AC arrow D. And what we want is AC arrow D, which is true. Okay, so F and E are equivalent. Is that clear? Hope you should be able to find equivalence of two functional set of functional dependencies. All right. So let's go up and see what all problems we have for our further discussion. So this is first part of my video where I showed you what are inference rules, that is IR1 to IR6. Okay, we have augmentation rule, we have additive rules, we have decomposition rule, we have pseudo transitive rule and transitive rule. So these rules we should be conversant with, and given a set of functional dependencies, we should be able to find out F plus. And if we have given two sets of functional dependencies, we should be able to derive each other's functional dependencies so that they are shown to be equivalent. Okay, so equivalent is a slightly difficult concept to understand, but once you work on these examples, we should be able to solve these kind of problems. Hope it is clear to all of you.